All right, so I think I got this up and running now. Let me hide that. So we're talking about ideal gases, and ideal gases. This is a picture my daughter drew of an ideal gas because when I asked my class to draw me a picture of an ideal gas, this was the best I got. So thanks for that, Mason. All right, ideal gases are going to follow the kinetic molecular theory, which basically states that the size of the particles in a gas are small, negligible in the compared to the size of the container that they're in. So as long as you don't have an atomic sized container, that's going to be pretty much true. So any container that you can actually see is going to be pretty large compared to the size of the atoms bouncing around in there. The motion of the particles is going to be rapid, constant, and random, which is pretty good, much true. And here's the problem, that all collisions between particles are perfectly elastic, which means that they don't attract each other. And that is not true because we do know that uh, there's some attraction among molecules. So if we go here and look at a gas, right? So here's a gas, and let's heat it up a little so that they're moving rapidly and all the things that we talked about. So they're small, hard spheres, they're moving rapidly. But if you look here, there's some clumping. They're not perfectly inelastic. There's a little bit of attraction among molecules or atoms, depending on what gas we're talking about. Right here, you see a big cluster. So that is where we fall apart, is this last rule. But if we assume those things, then we got this great law called the ideal gas law, which means the pressure times the volume equals the moles times the gas constant times temperature. Now, this is going to be true regardless of the amount because uh, we have a moles portion of this equation, and the one we were using before, which is P1 V1 over T1 equals P2 V2 over T2, assume the same moles. So now we have varied moles, which is good. But we also have this R, this gas constant. We solved this in class, and it turns out which gas constant you use, there's three of them due to the fact that they all uh, have a different unit for pressure. And since we couldn't really decide on one unit of pressure to use, that's why we have three different R's. So you're going to use the units of pressure from the question to determine which of these R's you're going to use. And the best way to do that is, frankly, if we just get rolling. So here's a question. We have 1 mole of a gas at 273 Kelvin and 1 atmosphere. So actually another thing before we get into that, the PV equals nRT. So the P and the R. So the P determines the R. The pressure will determine which R you use. The other thing that's important here is the V has to be liters, and the R we already determined. N has to be moles, not grams. So that has to be moles. Occasionally something in grams will be given, and you'll have to do a conversion. Please stop doing that. Not grams. And I have no idea why that's happening. And then the T has to be in Kelvin, must be in Kelvin. And think about it, because in Kelvin. There you go, caveman teacher. Must in Kelvin. All right, so sorry if any cavemen are watching. So here we go. I forgot what I was going to say, but I'm sure it'll come up again. We have, in this case, we need to figure out our P, our V, our N, and our T. So here we have 1 mole, and that's pretty obvious, our N, right? We don't have to convert that from grams. Our temperature is already in Kelvin. Oh, that's why. So we do this in Kelvin because we don't want negative temperatures, because that would end up with a negative volume or a negative pressure, and we're not really sure what that means. So there's our temperature already in Kelvin, so no conversion needed. Here's our pressure in ATM. So now we're looking for one of these R's that have ATM. And as you can see, this one has ATM, so that's the one we're going to use. It's looking for the volume, so the volume is equal to X. And when we find that X, it's going to be in liters. So this is the breakdown. Our pressure is 1 atmosphere, our volume is a question mark, our temperature is 273, and our moles is 1 mole, and our R is that. So if we plug this into the PV equals nRT, we will get that the pressure, which is 1 atmosphere, times the volume, which is X, is equal to the moles, which is 1 mole, the R, which we're going to use this 0.0821 to 1 liter atmospheres per mole Kelvin, and our temperature we're going to use as 273 Kelvin. So this is standard, right? That's the standard temperature, and that's the standard pressure. So this is basically at standard pressure and temperature, or STP. Now, solving for this X right here, where 1 times X is X, that's pretty easy. Notice, however, that our units are going to cancel. So here's moles, and there's moles in the R, so that cancels. Here's the, almost called it potassium, but that's Kelvin. There goes Kelvin. Atmospheres is on this side, so the atmospheres are going to cancel, and all that's going to be left is liters, and that's how we know the X will be equal to liters, because that's the only thing that didn't cancel. All right, so if we do all that, we get X is equal to 22.4 liters. And I got 22.4 by multiplying 0.0821 times 273. We get 22.4 liters. And there you have it. That is the answer for this question. And that tells us, which hopefully we're going to do in class tomorrow, that if you have a certain amount of gas, it's going to be proportional to how many moles there are. So water, which has 2 hydrogens, H2, and 1 oxygen. I'm going to change the color, and I did it the wrong way. My graduate advisor would be angry with me because he always likes oxygen red. But anyway, there's 1 oxygen for every 2 hydrogens. So that's why there's twice as much space here as there is here, because when you break water down into its component parts, you'll get twice as much hydrogen as oxygen. And since we just learned that gases occupy the same amount of space per mole at the same temperature and pressure, that's not surprising. Okay, moving on to problem number 2. I didn't want that much. Why is that all showing up? I don't remember that happening in class. But anyway, so I turned this into oxygen. How many grams of oxygen? When we were doing this in class, I did the mixture, and that seemed to throw some people off. All right, so let's look at this. We have liters, so that's a volume. We're looking for grams of oxygen. Pressure is here, 762 millimeters mercury. Body temperature is 37 degrees Celsius. So there's all our information. This is a pressure. This is a temperature, but it's not in Kelvin, so we have to add 273 to get it in Kelvin, so we get 310 Kelvin. All right, so we have a temperature, we have a volume, we have a pressure. The R we're going to choose based on the units of pressure, which are millimeters of mercury. So you can see this has millimeters of mercury, so we're going to use that R. Now I can make those disappear. And so now we got a pressure, we got a volume, we got a temperature, and we're looking for the moles. And from the moles, we're going to figure out the grams. So if we plug all this in, we got 762 for our P. Our V is 2.20. Our N is our question mark. So let me put that in a different color. So we'll do that X, right? So that's what our N is. And then our R is the 62.4. And our T is 310 Kelvin. So if we solve for that X, we got 762 times 2.20, and that gives us 1676. This is 1676. And then 62.4 times 310 is 19344. 19344 equals, and then the other thing that's left is the X. So I multiplied 62.4 times 310 to get that, 762 times 2.20 to get that. To isolate this X, I'm going to divide the 19.344 on both sides. So we're going to move that, right, divided by 19.344. That cancels here. And then over here, I'm going to do it again. And that's going to give me 1676 divided by 19344. Our moles, our N, is equal to, and I guess I should do this in blue because that's what color it was supposed to be, 0.0866. 0866 moles. Now the question's asking for grams. We have moles, and we said it was oxygen. So if that's how many moles it is, and we need to convert that to grams, so we're going to take that 0.0866 moles, and we're going to turn that into grams by dividing by 1 mole from the periodic table and 32 grams of oxygen. Oxygen being a diatomic, so it's 16 times 2. So that times 32 gives us, we have 2.77 grams of oxygen in fully inflated lungs if they were on fully oxygen. And that's the answer they were looking for. All right. Hopefully that made some sense. Here we go. Now we're in a better one. So we have 35 grams of carbon dioxide. Carbon dioxide is CO2. So that is going to need to be converted into our mole, right? We need to get this into the N to be moles. Let's call it moles, so it's a little clearer what I'm talking about. This 1550 milliliters is our volume. And because it's in milliliters, we got to get it to liters. So we're going to jump 3 places here. So our volume is equal to 1.550 liters. And then here is our pressure. So our pressure is equal to 0.250 ATM. And because that's ATM, we can look at these 3 and figure out which one we're going to use. And it's the one with the ATM. So we're going to use that one. So what I'm going to do now is discard all this stuff and then start again so that you can see that. All right. So our pressure is the 0.25. Our volume is 1550 milliliters converted to liters. So we jump to 3 places with our decimal. Our temperature is what we're looking for. It says, what is the temperature? So that's our X, and our moles. We took 35 grams of carbon dioxide. So if we have 35 grams of CO2, carbon, if you look on the periodic table, is 12 and oxygen is 16. There's 2 oxygens, so that's 32, and 12 is 44. So that's 44 grams in 1 mole. So that'll allow us to get to moles, and 35 divided by 44 is 0.795 moles. All right. So putting this into our PV equals nRT, 0.25 atmospheres is our P. Our V is 1.550 liters equals our N, which is 0.795 moles. Our R is 0.0821 to 1 liter atmospheres per mole Kelvin. And our T is what we're looking for, so we're going to make that a different color. T. All right. So notice here how things start canceling. There's atmospheres here. There's atmospheres on top here. So those units would cancel. There's liters here. There's liters on top there. So those will cancel. There's moles here. There's moles on the bottom there. Since they're on the same side of the equal sign, they're going to cancel. And the K is what's going to be left. So we're looking for that temperature. And that will be in Kelvin. So 0.25 times 1.55. 1.55 is 0.3875. So 0.3875 is equal to 0.795 times 0.0821 is 0.0652, 0.06527, let's say. And then that's going to be times T. So if we want to isolate that T, we got to divide both sides by the 0.065. So 0.3875 divided by 0.06527. T is equal to 5.94 Kelvin. All right. So the keys here are you need a mole value for your PV equals nRT. You need a volume in liters. You need a pressure in any of the 3 things. And whatever that is, it's going to dictate which R you use. So this is the R. And then the temperature always needs to be in Kelvin. I think that's all I got to say about that. I'm hoping that works. Let me know in class if it didn't.